everyone. Thanks for coming. My name is Michal Prevratil, and I'm the head of tooling and an auditor at Eki Blockchain Security. If you'd like to connect with me, feel free to follow the QR, or the tag is just MichPrev. It's on Telegram and X. And at Eki, we are blockchain auditors, but we also love building open source. Today, we'll be talking about Wake. But except for Wake, there's also a company and an extension I will also briefly show you today. And there's also open source fuzzer for Solana called Trident. Except for that, we also onboard new developers into the blockchain and the technologies. We have the pleasure to work with many amazing projects like Lido, Safe, Axelar, or for example, Aave and 1inch. And we've also received a couple of grants from Ethereum Foundation, Coinbase, and Optimism. Some of them helped to build Wake as the framework. So maybe you've heard about Wake before, maybe you haven't. Just to briefly introduce the framework, it's a Python-based open source framework for Solidity development. You can do testing in Wake, you can do fuzzing, which is like kind of special technique of testing when you use random inputs to stress your contract and hopefully find some interesting bugs and findings. And there's also the static analysis part where you can run built-in detectors to find some common issues that can be present in your code. And you can also define your own detectors in the framework and make them specialized to your own code base. There's also a language server, which means that, well, if you're using VS Code or Cursor, you would like some kind of support for Solidity, and for that you need a language server, and Wake is basically the thing that you need that's connected to your IDE, to the Cursor or VS Code, and it gives the basic support for the Solidity language. And for that, we obviously need the extension, so Wake also has a companion extension. And by the way, it looks like this. So I will show you again in the hands-on, but this is the extension. Now, if we take a leap back into the history of development of Wake, everything began in September 22 when the first version of Wake came out. Actually, this is not a typo. Originally, it was named Woke. It was not the best decision we've made, but originally it was named Woke. And it already contained a lot of modules, a lot of features. There was the basic compiler that was like built in above the Sol-C compiler. There was the language server, as I said before. There was some kind of initial draft of the fuzzer, and there were some built-in detectors to begin with. Then the next version was Woke 2.0, that was like in February 23, and at the time we've introduced a full testing framework that was kind of built on Anvil, Ganache, and Hardhat. So, well, you could write the test in Python, use these three development chains under the hood, and, well, stress your contracts either through unit tests or through fuzzing. The next version I have here is Wake 4.0, and now you may wonder where's the Wake or Woke 3.0, and that's quite a funny story actually, because in the February 23 we've released the testing framework, but then we've realized that there are some blind spots in the API, how you work with the framework, and that we would like to change the API a bit, and that's why we've created a new version 3.0, the breaking change, 1 month later in March 2023 to fix the mistakes and make everything right. So that's why that version is not here specifically. And regarding Wake 4.0, this is the time that we've made the rebrand and we've renamed the framework to Wake. I think it was for the better. And together with the rebrand, we've also introduced the static analysis framework so that you can write your own custom detectors on your code base. Last year, we've introduced the first release candidate of Wake 5.0, and the main change is that we've taken the original testing core of the framework and we've rewritten the whole framework into Rust. So you can still write, and you have to write the tests in Python, but the core is now written in Rust, so you call some functions in Python, and it's kind of translated under the hood into Rust or wired into Rust. And so it's amazingly fast. There's like 10x up to 80x performance speed up, but the API is basically still the same. It's just more powerful than before. And now we are in the AI era, and so there are some features that I would like to introduce into the tool, like MCP server with static analysis for solidity, so that AI can list all the contracts, functions, filter those functions and contracts, and it can, I don't know, it can give you the amount of codes that you've written, like in the size of bytecode, so you know how much space you have left or not. It can generate, or it could generate some tests or fix issues it has found through the detectors. Now let's move a step closer to fuzzing. So maybe you know, maybe you don't know, but fuzzing is kind of special technique when you use random inputs, generate random parameters, generate random sequences of functions, and this way you are trying to find some interesting bugs. And well, the most common question that I get when I'm doing this kind of workshops or talks is why we should test in Python, especially in 2025 or 26. And well, in my opinion, it's better to have general purpose language because Solidity was never meant to be a testing language. And while it's quite good in some cases, especially for unit testing, you may be missing some powerful features of the general purpose language. Like when you are mirroring your state of the contract, then well, when you have the same language, you will most likely write it in the same way, and this is not very beneficial because you are most likely just copying the bugs from one file into another. Also, some complex assertions may be quite problematic, or even logging of what's happening inside the contract just for debugging purposes. Some projects have quite complicated math behind the idea, and this math has to be somehow translated into Solidity because, well, Solidity doesn't have floating point numbers. It even doesn't have fixed point numbers unless you kind of emulate with decimals. So you have to translate the math in some kind of way, and for example AM curves or interest or vesting, and that's something that's non-trivial. And again, when you test again in Solidity, you most likely copy the same bugs, the same mistakes. But if you take a completely different language that has unlimited precision for whole numbers, and it also supports floating points, it supports decimals, you can rewrite the logic in quite a different way and compare your Python logic to the Solidity code. One important thing from my point of view is that you often need some real data structures like queues, data classes, and this kind of stuff. And this is not present in the Solidity, and you have to somehow emulate or write it yourself, which is annoying. It increases the code you have to maintain, while in Python you have everything prepared and it's just ready to be used. I've got a, and yes, one more important thing actually. Solidity means that you often encounter stack too deep, but you also have to recompile on each edit. So each time you update your test, you have to recompile and you have to somehow rewrite your test, which is quite annoying. I've got a couple of examples here. So let's say that we want to track the balances for a couple of tokens, and for each token we want to track the balances of each account we are tracking. So in Solidity you will most likely use some kind of nested mappings, but you cannot iterate over those mappings because Solidity doesn't support that. While in Python we have just dictionaries, it's very easy, and you can iterate over all those dictionaries. So you can list all the accounts or all the tokens that are somehow tracked in the state. Another example, if we wanted to somehow track the pending queue of withdrawals, again in Solidity we don't have some kind of queue like an internal structure, but in Python there's the queue, which is especially used for, or can be used for that. So Again, much easier and less logic that you have to write. Or if we just want to list the addresses that have more than 1,000 chars, in Solidity you have a loop that you write yourself, while in Python it's a one-liner and just less code and easier to write. Or another example is debugging logs, where you will most likely use console log in Solidity. You may need to API encode depending what exactly you want to log, while in Python you just print with the formatting syntax, and it's super easy. Now let's move on to how we write fuzz tests in Wake. I would start with invariants, which are basically assertions. These are the properties of your project that should be always true, and you want to check them, well, most likely after each transaction, but at the end of the day, it's up to you when you want to check, how frequently you want to check those invariants. However, they are assertions, something that should be true in all the cases. And this is how you should usually find the bugs. You can also make another assertions, not as invariants, but let's say stateless assertions when performing some transactions. And there's also one class of bugs or issues that can be discovered with wake fuzzing, but you don't need to write any assertion. No assertion, still you can discover bugs, and those are denial of service issues. So if you send a transaction and you don't check the result, if it reverted or not, you are possibly missing denial of service issues, because, well, you should assert about the state of the transaction as well, and I will show you later through the workshop. Anyway, this is the syntax. So in Wake, each fuzz test is a class, and so it has methods. Invariants are automatically checked after each flow, which is like an independent step in the fuzzer. These have to be decorated with the invariant decorator, and I usually use the invariant prefix just to make it clear it's an invariant, and inside you can define any Python logic and it will just execute after each flow of the fuzzer. Now, when we move on to the flows, this is one example of a flow. As I said before, flow is like one independent step in the fuzzer. So the fuzzer has, like, let's say, a couple of options what it can execute given the number of flows you have defined in your test, and it will randomly pick one of the flows you've defined. It will execute the flow, and after the flow it will execute all the invariants. So I hope this is clear. And inside the flow, again, you can do whatever you want to, but usually you want to send one transaction. That's the core transaction, what you are executing or doing. But for the transaction, you need some kind of input parameters. And, well, so you need to generate them. And as I said, fuzzing is about random data. So you generate some random parameters you pass inside the function, inside the transaction. And this way, you define the flow. And then this is purely optional. However, I find it very useful and like the basic part of fuzzing in Wake. And this is the state tracking. So you don't rely on the state of the contract. You don't rely on the storage variables inside the contract. Instead, you keep your own Python state saved inside the class, inside the Python, and then in invariants you compare your Python state to the state in the contract, and this way you are basically doing differential testing. So we are comparing your mental model that you've redefined in Python to the actual state on chain in contract. This is how the state machine looks like. Again, as I said, the fuzz test in Wake is a class. So you can see there's a class. It inherits from the fuzz test, which is built inside the framework. There's a couple of hooks you can define that are executed at specific times during the lifetime of the fuzz test. The most important one that we will be using today is pre-sequence, which is like the first initial step before everything begins, and this is where you should initialize all your like initial Python state, and this is also where you must deploy your contracts as it's shown in this example. Then you can define a couple of flows. So I have just some placeholders here, and finally also some invariants to be executed after each flow. Except for the class, there's also an entry point because Wake is built on PyTest, which is the testing framework for Python in general. And so you need an entry point that will be executed. It's called test my token here. And inside the entry point, we just create an instance of the fuzz test, and we pass some parameters to the run method, which specify how many times we want to independently test the contract. So one independent run is called a sequence. It's shown in the image here. And after the end of the sequence, we completely reset the blockchain state and start from the very beginning. So we again execute the pre-sequence, again deploy all the contracts and start from the beginning with some new random data and new stuff to be explored. So this is the sequence, and the first parameter inside this run function is the number of sequences, so number of independent executions. The second parameter is the number of flows, which is how many flows, how many these flow functions you want to execute during one sequence. And this is what the image actually describes. So at the beginning of the sequence, there's the pre-sequence where you deploy your contract, you initialize your Python state, and after the pre-sequence, the first flow is executed. This is chosen randomly. After the first flow, all the invariants are executed to check that the state matches the state in the contract on chain. And after invariance, the second flow executes, and invariants are again executed, and this follows as long as you have some flows to be executed given this number of the total flows you want to execute in a single sequence. After that, the chain is reset, and that's it. So this is the state machine. Except for like writing your test, you will obviously run the test, and after that you can check the code coverage inside the companion extension. So this is how it looks like. Maybe I will show you once we write the fuzz test, but well, basically you can see the number of executions of each statement or each line, and this way you can easily see what branches were not visited. So I believe we can move on to the hands-on. So if you want to follow, please check the link with the example, with the workshop, clone it, and check the initial steps. I will walk through them again once I change to the terminal. Or if you just want to follow later, you can check the QR code and check it at home later. By the way, how many people want to follow? Just that I know if I should wait or I would just present and then you can check out later. Okay, so I guess I can begin. So I will switch into my cursor. This is the project. It's a very simple one. There's a couple of files already prepared. There's, by the way, CloudMD. I won't be using this one, but if you want to try your code just to generate the fuzz test on your own, you can point it to this file, and it should generate some fuzz test on its own, so you don't need to type any single line of code, actually. Except for the CloudMD, there's the package.json because we need some dependencies to be installed. There's the wake config, some kind of basic README, and 2 contracts to be tested. I won't show you the contract because, well, when you are doing fuzzing, you don't want to go too deep into the logic of the contracts. You just want to check the interface, what functions are available, and based on that, you will execute something, and you will observe how the contract behaves, what are your expectations, and this way you are unbiased and you will easier find some big issues. So let me switch to the terminal. I hope it's well visible. So in order to install Wake 5.0, you need to type pip3 install if wake equals 500 RC2, because we'll be still using a release candidate of Wake 5.0. So let me run the command. It was very quick. I had everything pre-cached. And now if we type wake -- version, we should see the version of wake we have installed. The next up, we need to install the dependencies. So I will install them with pnpm. So it was again very quick. I had them already installed. And this is the initial setup. So we have wake installed, we have installed the dependencies. Now, if we move on to extensions that I'm recommending, we definitely need a Python extension because we'll be writing tests in Python, so I definitely recommend the Python extension. It depends if you're using Cursor or VS Code because there are slightly some differences between the available extensions. And except for the Python, we may use even better TOML for the wake config file. And obviously, and most importantly, we need the extension for Solidity, which is called Solidity Wake, and this gives the basic support for Solidity into your IDE, so you can navigate over the code, you can see the syntax highlighting and generate control flow graphs and see, for example, detections of some issues that you may possibly have in your code. Now I will create a dummy test file, so let's call it test vault.py because I can see that there's a vault contract in the code base. Let me type some basic imports that we need basically every time we are doing fuzzing in Wake. So from Wake testing, we want to import everything, and also from Wake testing.fuzzing, we again want to import everything. So the first import imports the basic stuff that can be used for unit testing, while the second one contains specifically some symbols that will be available and needed for fuzzing. As I showed before, a fuzz_test is a class in Wake, so we'll define a vault fuzz_test class that inherits from fuzz_test. And let's put pass here just to make it better later. Now we define the entry point because, as I said, we'll be using PyTest under the hood, and so we need the entry point for the test where to begin. So let's call it test vault. And inside the function, we will create an instance of our fuzz_test. And we will call run, and let's say that the sequences number will be 10,000, and the number of flows, for example, 20,000, whatever. So this is the basic setup, but the most important thing is that we need to launch the development chain. So far, we've only written some code in Python, and it doesn't do anything, actually. So we need to launch the development chain, and for that, there's a built-in global variable called chain, which represents the default chain that you'll be using most of the time. And on this chain instance, there's something called connect, and this will launch a new development chain instance. If we used Anvil, it would launch Anvil, which is like a local development node as a part of Foundry. However, if we check the Wake config file, there's REVM. As I said before, Wake 5.0 comes with its own Rust execution engine that's built into the framework, and it's based on REVM, which is Rust EVM as a separate project that's maintained. So we'll be using this Rust-based execution core. And so it won't launch Anvil, it will just use something inside. And this way we will connect to the development chain, and we are ready to deploy some contracts. So let's define the pre-sequence hook. And inside the hook, we want to deploy our contract. As you can see, there are two contracts, mock token and vault. So we definitely need to deploy both of them. However, how do we do it? How do we actually do it? So we need to generate a typing stubs. If we call wake up PyTypes, this single command will compile all the contracts inside the project, and it will also generate something called PyTypes, which are typing stubs for the contracts and events, errors, structs inside them. So it will generate this PyTypes directory. It's not meant to be human readable, but it's very useful for the linter inside your IDE. It's also quite useful for AI agents to check how to actually execute the functions on contracts. And there are three directories. There's Wake, which contains some built-in interfaces and contracts ready to be used. There's also OpenZeppelin, because we are using OpenZeppelin as the dependency of our contract. And finally, there's contract, which represents this contract directory. So the structure of PyTypes follows the structure of your project. And inside you can see there's the same files, but with the Py extension. And as I said, this is not meant to be human readable. It's just there so you can execute or invoke the functions, but not meant to be read by human. Since we have generated PyTypes, we can import from PyTypes from the module, from the directory, and we will be importing both contracts, which is the vault, and the mock token. Both of those, since they are contracts that can be deployed, have the deploy function. So if we call vault.deploy, this will execute the constructor of the contract. And it has the same parameters as the constructor. So we need the asset for the vault. We need some kind of treasury. I don't know what it means, but it's some address or an account. And we need a fee in BPS. So let's say that the fee will be a random integer, in between 0 and 10,000, which should be the maximum. And for the rest, we will need the asset, which will be our mock token. So let's deploy the token first. Mock token.deploy. And we can use, let's say, this name and symbol. It doesn't really matter. Once we have the token deployed, we can pass it to the constructor of the vault. The next parameter is a treasury. For this one, let's choose a random account. So self.treasury. Treasury will be random.choice from chain.accounts. When you launch a new instance of a chain, there will be a predefined set of accounts that you can already use. By default, it's 10. You can easily override the initial number of accounts by specifying this parameter. So you can, for example, start with 20 accounts. It's up to you, but I will just keep those initial 10. And this way, we will choose a random account from the initial set of accounts, and we will say that this is the treasury that we will pass into the vault, into the contract. And the final parameter is a fee, which we have already randomly generated here. Now, let's save this file and run the fuzz test. It should just kick off the instance, the chain, and it should deploy the contracts, and that's all. So if we type wake test/test vault, I like to append -d for debug. So if we encounter any exception, it will enter an interactive debugger in Python, which is very useful because we can inspect what actually happened. And I like to append for extra verbosity, so we can see all the assertion failures and this kind of stuff. And this is expected because it ran successfully, but it didn't find any valid flow it could execute, and so it raised an exception. So it runs correctly, but we have nothing to execute except for the deployment of the contracts, which on its own is not enough. All right, so let's define the very first flow to be executed inside our fuzz test. As I showed you in the presentation, it has to be a function decorated with flow, and since I already know the contract, I know there's a function called deposit. Let's keep it simple like this. But if I didn't know, I could just open the contract, and with the extension, you have everything highlighted. There you can see already some vulnerability possibly in your contract that was detected by Wake. And there's also plenty of labels that you can click on, generate some graphs and whatever. But the feature I want to show you today is public functions, which is above the definition of the contract. And if you click on it, you will see all the public functions except for pure and view functions. Even through inheritance, if we had some inherited contracts, we would see all the functions, including those inherited ones. And these are the functions that we can call. So again, we don't need to inspect the complete logic of the contract. We can just see there's deposit, there's withdraw, there's transfer. That's all we need. So we will start with the deposit. And since we already have the instance of Vault, and before we begin, what I also like to do is just for the type checking and for the linter, explicitly specify that we will have a token variable assigned here. So there will be the token in our local Python state. There will be the fee, which is an integer. There will be the treasury, which is an account. And there will be the vault, which is the vault we've deployed. Now we can execute the transaction. So we will call self vault.deposit. But we need some input parameters, and this one specifically represents the number of assets of the tokens that we want to deposit. And what's also useful, and I will also almost say required, is to specify the sender, because if we don't specify the sender, the default one will be used, which is not very random, and we want to do random testing. So we also want to generate a random sender. So the sender will again be a random choice from chain.accounts, which is the initial set of accounts we have available in the instance. Now let's generate the amount. It's actually the amount of tokens that we will deposit into the vault. Let's begin, let's say, with a random integer in between 0 and 1 million, for example. And this will generate an integer in between those two bounds, including those bounds. However, the probability of each of those numbers to be chosen is the same. It's uniform, which is maybe something that we don't want to test because the 0 may be an interesting value for our fuzz test. So let's say that the probability of generating 0, it's let's say 1%. Should be enough. We are using floating points, so it's 0.01. And this is much better for fuzzing because we now have increased chance that we will generate 0 as the input parameter for the function. And we can pass those parameters now inside the deposit function. So we will send the amount. We will specify from as the sender who's sending the transaction. We can now even execute the code, but it won't be super interesting because it will just revert. Maybe it's still quite interesting because we can inspect why it reverted, but I think it's quite clear because we've said that we will send this amount of tokens. You can actually print the amount. So this is the random number we've generated. So it says that we will send this amount of tokens into the vault from the sender, which is this address. However, we didn't give any allowance for the vault to pull our tokens, and so it will obviously revert because it cannot pull our tokens. We don't even have those tokens, so it's not possible to deposit this amount. What we need to do as a part of testing, this is obviously not possible on the mainnet or even testnet, is that we can call a cheat code that's called mint ERC20, and it works for almost every token, ERC20 token out there, where the first parameter is the token that we want to use, the second one is who will receive some extra tokens, and the final parameter is the amount of tokens that we want to generate for that given account. And this is a cheat code that only works on a local development chain where we can change some stuff we wouldn't be able usually. And this will generate our tokens. Since we have them generated, we need to give the approval. So we will call on the token, self token approve. We want to give the approval to the vault and specify the amount we are approving. And again, super important, we need to specify who's giving the allowance, who's approving the pooling of the tokens, which is the sender. It is the same account that's later calling the deposit function. I will save it, and let's see what it does. And it reverted again, but this time it took longer. Maybe what will be better, before we discuss this one, is what I also very much like to do is to add some basic logging into the fuzz test. So let me briefly create a logger that will log some basic stuff happening inside the fuzz test. And after each flow, it's a good idea to log what happened inside the flow and what we've performed. So we've deposited this number of tokens from sender. We can just use sender like this. We don't need to use the address. And we've deposited to the vault. I will run the test again. One more cool feature, there's a random seed. Each time you invoke wake test, it will generate a new random seed. And if you have already some seed pre-generated and you pass it on the command line, it will reproduce the same sequence of operations of transactions as in this run, because it uses the same first initial seed of random operations. And so we should encounter the same error sooner or later, because we are reproducing the same scenario of operations on the blockchain. And as you can see, it performs a lot of operations before we reach this zero amount revert. So we've performed a lot of deposits into the contract, and then we've got a revert from the transaction. This line sends a transaction because we are calling a deposit function that changes the state. So that's a transaction that we are sending to the chain. And if there's a revert, which means the transaction failed, it will automatically pop up as an exception inside the framework. So if we check the vault and inside the vault zero amount, we would see that there's the same symbol defined, which is the error of zero amount, and it's the same name, and even the parameters are empty. So it's the same thing that we've seen on the command line. So even these errors and also events are regenerated from Solidity into Python through the PyTypes. Now we can possibly inspect what's happening, but I think it's quite clear. So let's print the amount. And it's actually not quite clear because the amount is non-zero, but we've still received the reward. So we should probably inspect deeper. And for that, I don't want to dive into the code of the Solidity, because that's something we shouldn't do when doing testing, when doing fuzzing, because this way we would be biased about the code because we've already seen that. Instead, let's proceed and we will evaluate later. So Just by looking at this vault and maybe the description, it's quite clear to me that this is like ERC-4 4626 based vault where we deposit some tokens, we will receive shares, and then later we can burn those shares to receive back the tokens. And so let's compute the number of shares that we should receive. Let's compute it before this line, because if we compute it after, we would never reach the computation in the branch when it's reverting. So we wouldn't be able to print the number of shares. And so now it depends if we are the first initial depositor or not. For that, let's trace the number of shares we have already distributed, which can be a dictionary with the keys being accounts, the holders of the shares, and then the number of shares they are holding. I will use a default dictionary, which is like special structure in Python that very much emulates mappings in Solidity. So even if you have a key that was never accessed before, it will default to a default value that you define. In our case, it will be 0. If we pass here int as an integer, it will default to 0. So if we ask for any account, even existent, non-existent, whatever, it will always return 0. So if the sum of shares we have already distributed is 0, it means that this is the first deposit into the vault, and so the formula is a bit different. First of all, let's compute the fee, because the fee, as I assume, is just a percentage of the amount, and since it's in BPS, we should multiply it by the fee number and then divide by 10,000, which represents 100%. Now, the number of shares will most likely be the amount minus fee, because the fee is not the part of the deposit we are making into the vault. Otherwise, the shares number most likely will be the amount minus fee and then multiplied by the total number of shares we've distributed so far, and divided by the total number of assets that's held inside the contract. For now, we can just use self-token balance of the vault. So we have computed the number of shares we should receive, and if I run the fuzz test again, it should take some time. But now, if we print the number of shares, it's on 0 actually. That's interesting. So let me check the formula again, and I believe I know why it's non-zero, and it's because of a bug that's present in the contract, and I've reproduced the same bug inside my code. But, well, let's correct the formula then. Because this is not very precise. If we check the total number of tokens inside the vault, we are also accounting for the fees, because the fees are also transferred into the vault, but we shouldn't account for them when computing the number of shares. So this is obviously a bug that may be present inside the contract, but it's definitely present in our fuzz test. So when you are doing testing of the contract, you shouldn't do the same mistakes inside your fuzz test code inside Python. So let's track the actual number, like let's say total assets, which will be an integer. It will be 0, and we will update the total assets number by the amount minus fee. And what's also important, and I forgot to update, is the shares number. So we should say that the shares held by the sender after the transaction is finished is updated, increased by the shares number we've computed before. And I forgot to update this part of formula, obviously. We shouldn't rely on the on-chain state. Instead, we should use our local Python state. So this is the local number we've computed inside the fuzz test. And it's still printing as non-zero. Never mind. So let's debug what's happening. We still have some time. So let's deposit, or inside the deposit function, let's actually add some console logs, and I can at least show you how we can debug what's happening inside the contract. So we can insert some console logs into the contract. We can import, or we need to import the wake console, so it resolves those functions. Since we've updated the contract, we need to recompile and to regenerate types. So we need to call wake up types again to recompile, regenerate, and now we can just run it all again, and we can inspect what's happening inside the contract. And if we, for example, use chain.txs, which is the global list of all transactions we've executed so far, we check the last one that we've executed at this line, and we check the call trace property. We can inspect the call trace of the transaction, and we can see the console logs we've inserted into our code. And here specifically, we can see that we are calling vault at this address. We are calling the deposit function. We are setting this number of assets as the input. Then inside this vault, there's a balance of call performed on the mock token. There's some value returned from the token. The first console log we've inserted says that the balance before is this number of tokens, and the second console log says that the shares number is 0, which means that inside the contract, we are actually seeing the 0 number of shares. However, in our fuzz test, it's a different number. And this is something we should focus on, because our expectation is that we would see this number of shares, which is 12, but inside the contract, inside the contract we are seeing, based on the console log, 0 number of shares. So this is something different than we expected, and we should investigate. In this case, it will be a bug in the contract, but it could be, as I showed you before, it could be a bug in the fuzz test as well, so that's why it's needed to be investigated. However, this is how we find bugs inside the contracts, that we basically follow the signatures of the contracts, we execute some functions with our assumptions, and then we compare the differences between the contract and the local Python state. So I would wrap it up for today with this hands-on. If you want to follow, if you want to generate a full fuzz test, you can just say, hey Claude, generate the fuzz test for this contract. It's super easy because there's a Claude MD file inside the repository. And I will just briefly switch back to the presentation, because Wake is now listed as a part of the Ethereum security quadratic funding, which means that people can donate to various projects. I recommend you to check all the projects, because there's many of interesting ones. There's the Wake framework also listed with the extension, and based on the donations from people, the tooling then gets some funding from the DAO that's organizing this funding. And specifically for Wake and the extension, the funding will be used for the static analysis MCP, so AI agents can inspect the code and see some insights into the code, like control flow and where's the given variable being used. And the next goal is also to kind of support AI fuzzing, so we don't need to write this manually, because as you can see, we can still make some mistakes. Instead, the AI can write this kind of fuzz test, and it can debug what's happening and be much more efficient than we are. And finally, as I said, Wake has also some static analysis detectors that can detect some common issues, and we can let AI fix those detections and propose some relevant changes. So if you want to support, these are the QR links. Be sure to check all the projects, because there's many interesting ones. And one final note, please check out also the talk from the CEO of Eki Blockchain, who will be presenting our approach to benchmarking AI on the smart contracts. And this should be in like an hour in the Gregor stage. So please also check that as well. And yeah, that's all from me today.
Okay. Thank you, Michal. We have a time for some quick questions. Anyone with a quick question? If not, then you can catch Michal in the halls, and we invite everyone to come listen to Gregor's stage in about an hour. Okay?